Good afternoon, everyone. I'm Brandy Brown, SCTE Rocky Mountain Chapter Secretary. I'm excited to introduce to you today a webinar on fiber optics basics and fiber test equipment, featuring our guest speaker, Kendall Robinson, who I will introduce to you shortly. Before we get going, let me take you through a few key elements of SCTE and Rocky Mountain Chapter. The Rocky Mountain Chapter was recognized at 2022 CLC, receiving 8 awards for 2021 success, including Chapter of the Year Award. We are continuing our efforts in 2022 in alignment with our chapter mission, and in a moment, I'll tell you how, as we speak about our membership opportunities and how we grow our community. In joining us today, we want to ensure you understand how to stay engaged in the future. Your membership does not usually auto-renew, so please ensure that you log in to the website so that you don't miss out on any opportunities to maintain your activity, your status within the wonderful organization. By doing so, you want to ensure that you're checking in with your organization to ensure you take full advantage of all the opportunities available to you. Additionally, we want you to share any of the opportunities, share with colleagues about SCTE and ways to encourage peers to join us. Some of you may know, and we want to ensure everyone is aware of SCTE and what SCTE offers as far as the variety of certification opportunities, which are the cable industry's premier endorsement for professionals. Additionally, the Rocky Mountain Chapter Certification Program, Additionally, the Rocky Mountain Chapter Certification Program incentive includes reimbursement for successfully passed exams. We encourage everyone to take advantage of this program. So here is a brief description of the certifications offered. SCTE offers industry certifications for all areas of the cable network ranging from installer to engineer. Certifications not only promote your expertise, but support your career advancement. Please visit the website, either scte.org or scte-rmc.org for additional information on certification opportunities. Finally, we want to offer you ways to stay connected to SCTE and the SCTE community. Be sure to connect with the SCTE Rocky Mountain Chapter via any of these methods of communication, whether it's Facebook, Twitter, email, website, scte-rmc.org, so that you can connect with people and organizations by way of all of these methods of communication, using all of the resources to network with local members, industry partners, and the community at large. Now, for us to welcome our guest of honor. Please help me welcome Kendall Robinson. Kendall Robinson has worked within the cable telecommunication industry since 1991. He has a strong industry knowledge of various cable technologies that revolve around test equipment for fiber optic testing, RF leakage, DOCSIS, return path maintenance, head-end, hub, and field maintenance. Pardon that, Kendall. Over his tenure in the industry, Kendall has worked for many companies, including Tektronix, WaveTech, Viavi, Sunrise Telecom, Greenlee, Textron, and Devisor. Correct me if I'm wrong there, Kendall. Kendall now works for Jones NCTI as a curriculum developer and as a subject matter expert, and brings 30 years of industry knowledge together to develop training material for the communications industry. We are so excited to have him here, and we'll now be handing it over to Kendall. Thank you so much, and we're excited to have you here, Kendall.
Thank you, Brandy. So I thought I was going to do my own intro, so I appreciate that. So I was asked by the Rocky Mountain chapter to present the course in fiber optic basics, which I'm going to do. And also apparently there's some Cascade Range chapter folks on the call as well. So welcome to you guys as well. So the fiber optic basics and fiber test equipment is what I'm going to be talking about. The presentation is going to be foundationally for new technicians, but I've tried to make the content interesting enough for all levels. So hopefully some of the fiber pros out there will find this interesting as well. So this is the agenda: fiber intro, fiber connectors, ribbon cable.
Hey, Kendall.
Yes.
We're not seeing your screen yet.
Oh, I'm so sorry. Thank you. How's that?
There we go. That's perfect. Thank you.
Learning problems. Okay, there's the agenda. Fiber intro, fiber connectors, ribbon cable. As a little segue, fiber safety, fiber test methods, and just some ins and outs of the OTDR and some of the test results. So there's a lot of interest in fiber these days. The reasons are driven by the demand for more internet speeds, by the residential service operator and mobile providers. Fiber is being, of course, extended closer and closer to the home, and in terms of FTTH. And over the last several years, backhaul has been transitioning from the legacy transport networks to carrier Ethernet. And we're now seeing direct connections of fiber to the antenna as well. So, and NewPON and RFOG fiber installations are taking fiber closer and closer to the home. Of course, those have been going on for several years. CWDM, which is coarse wave division multiplexing, we're hearing a lot more about. Popularity in that is increasing due to the fact that it's a lower cost to deploy for the metro networks. And DWDM, dense wave division multiplexing, of course, is used for longer haul. It's kind of used intermittently depending on density, but ultimately it's a more expensive deployment. So CWDM still wins in terms of pricing. Just turning the laser pointer on. So a single mode fiber can be identified here by the yellow jacket. The orange jacket to the right is for the multi-mode fibers. And here, in terms of the fiber, it consists of a core, followed by the cladding, and then there's an outer layer that is encased in a buffer coating material. So the center core is what is carrying the light, this portion, in this small portion of the fiber. And the cladding surrounding it is also made of glass. And the reason it stays within the core is because there's an index of refraction difference. So it's got a lower refractive index, causing the total internal reflection to occur at that point. So right where the cladding meets the core is that refractive index difference. And the outer buffer coating right there, this is the piece. If you're cutting a piece of fiber and you're shredding it back, this is the part that takes a little bit more skill when you're trying to cut this off. You usually have to turn your blade at 45 degrees and pull it off and get that residue off with a little bit of fiber on a cloth. So let's talk about the Fiber Connect polishes. The one on the left-hand side, the PC or physical contact, it is flat, but on the edge it's got a little slight dome. This is probably not something you'll come across too much. This is actually a multi-mode patch, using multi-mode patch cores, and it's going to have a white connector, white jacketed connector. The next one across to the UPC or the ultra physical contact polish. This is basically what we call the flat UPC connector. That's going to be a blue connector, which indicates that it's flat. And then finally on the right-hand side is the APC, so the angled physical contact. Some people call it angled polished, but the correct term, in fact, is angled physical contact type. In terms of pulling these connectors in and out, the flat UPC is going to have a lot more wear and tear occurring on it when you plug it and unplug it. The APC is a lot more forgiving as well. It's going to be able to endure a lot more connections and disconnection cycles than the UPC. So that's one benefit. But the main benefit on the APC is the fact that it's got a much better return loss, down to about minus 60 dB versus the 50 on the flat UPC. And this is a warning for those of you plugging an APC connector in fact, or even a UPC. Typically, like at an OTDR, you're going to have a flat connection, a UPC interface. But if you have an APC in your hand and you plug it in, you can cause a lot of damage to that connector. So be very careful. Now you want to have an APC connection on the OTDR. We'll talk about that in the next slide, but be very careful. The cost of a bulkhead is thousands of dollars on an OTDR. So if your OTDR is priced around $5,000, the bulkhead is probably 30–40% of that cost. You don't want to damage the bulkhead. So this is the SCPC contact. SC stands for snap-in connector. The internal ferrule is 2.5 millimeters, and it's widely used because of its excellent performance. So it was a connector standard in 1991, but was not used widely. We didn't see it used very much because it was quite expensive. The price of this compared to the ST was a lot more expensive. Now it's no longer that price, and this is definitely the most popular connector that you'll find out there. And back to the OTDR, like I said, you want to use the APC connector, and here's the reason why. You want to use the APC for its reflective benefits. Well, obviously, if your bulkhead is flat, it's not going to make any difference. So if you're ordering the OTDR, you want to order it with an APC. That would be where the benefit happens. So in terms of minimal reflectance, that's where it would occur. And the other thing that certainly is a recommendation is keep that connector, that APC connected on there. Don't unplug it and disconnect it. Try to find a way to keep that jumper on your OTDR if possible. So we're going to jump through some of these connectors just pretty quickly. LC is the smaller one. LC stands for loosened connector. Much smaller form factor. It's a 1.25 millimeter ferrule, and you'll have to remember the different sizes, and I'll explain why in a minute. But this is half the size of the SC connector. So it's got a pretty much standard ceramic ferrule contact, although smaller. So as you're aligning it, you'll know it's terminated. Push it in. When you hear the click, it's perfectly terminated. And performance is good. It's highly favored for single mode, hence the color blue. So in head ends, data centers, you'll see these. That's where space is of a premium. And when you need to fit a lot more density in, LC is the way to go, of course. Just a little bit of history on some of these other connectors. So FC, the Frank Charlie. This used to be the most popular single mode connector for many years. 2.5 millimeter ferrule. It had an advantage. It was a very screw-on, very, very firm connector. So you plug it in and you turn the screw to make sure that you have to align the key slot and then tighten it. So it was a very secure connector. Pretty much being replaced, and there's probably very few out there still being used, being replaced mostly by SCs and LCs. Again, a little bit of history. The ST, that was a straight tip connector. This was actually an AT&T trademark, and it's got an orange cable on there. So if you notice that, that means it's multi-mode. So still probably a lot of these are multi-mode. The connector's got a bayonet connection. The center ceramic ferrule is 2.5 millimeters as well. If you're working in a data center and you've got different multi-modes, you'll be using these. The benefit of 2.5 is you can use a mating adapter, and it's spring-loaded. You'll be able to cross-connect STs, SCs, and FCs pretty easily with that cross-connector. This is an MPO connector. I think I saw the first MPO connector several years ago. And it basically means multi-position optical. That's what MPO means. There's sometimes it's called an MTP, which is its commercial name, MTP connector. So here, the one on the left on the bottom is a 12 fiber connector for ribbon cable. And the bottom right shows a 24. So there's 2 rows, each one being 12 fibers. The MPO can be joined together with this adapter. And the fiber ferrule is alignment here with pins. So you've got pins on one side and holes in the other. And the alignment indicator is the white dot, which you'd see on the side. Really, there's only one way to plug it in, but the white dot means it's position number 1 on the pins. Mainly, MPO connectors are used for pre-terminated cable assemblies, cable systems using ribbon cable. So ribbon, many advantages. Ribbon cables, typically they're found in groups of 12. And the main benefits is it can help the technician perform easier and faster mass fusion when splicing. You're obviously reducing time, reduce cost of installation, and overall your fiber restoration is a lot quicker with ribbon fiber. Older fusion splices may not have adapters, but new ones certainly do. So there's adapters for ribbon cable. So not just for splicing 2 ribbons together, but also you can, in many cases, you can do a fiber stub MPO connector so you can join a ribbon to a connector using that adapter in the fusion splicer. There is a downside to ribbon. So you have limited motion. You can only bend it in the longitudinal axis. So, and since there's no control over how the ribbon is oriented inside the cable itself, you could be bending the fiber, could be perpendicular to its longitudinal ribbon axis. And in that case, you'd be putting stress on the fiber and causing damage. So the way that this is minimized, ultimately the rule is try never to bend ribbon cable. But the way they minimize this is to overall strengthen and make the ribbon cable stiffer, and that is done intentionally. The stiffness on the ribbon cable is done to deter technicians from bending the ribbon cable. So let's talk a little bit about safety. So laser safety is critical since you're looking at all different kinds of light and mostly invisible light. And so you have 3 classes of lasers. So OTDRs, by the way, they use class 1. And usually when I mention this, people are like, oh, it's a safe class, so I don't have to be that careful. Well, you do. So class 1 is what the OTDR is, and it is the safest class of lasers to the human eye. In fact, it is considered lowest risk. The other classes are class 2, low risk, class 3, moderate and high risk, and 4, extreme risk. And even though the OTDR, as I mentioned, is class 1, you still need to observe these 3 safety precautions. So never look into the laser output port, avoid looking into the pigtail or the end of the fiber. So you don't want to be looking at see if there's dirt on the end of it when it's turned on. Of course, always turn the OTDR off when you're not using it. Be very mindful of all of those steps. And one other thing, the lasers directly will be classified in 2 things, power level and wavelength. And both of those are very, very important. So these are the questions you should ask yourself. Is it visible or is it infrared? Does it have short or long wavelengths? Is it high powered? Shorter wavelengths, by the way, are a lot more dangerous. So, because it's got a lot more concentration on the retina. And remember, here's the other part. The reason you want to be extra careful. You get into these routines of being safe around the class ones. You will definitely come across all of these in the field somewhere. So if you're touching DWDM, those transmissions are class 3 lasers, and they're more powerful than an OTDR by a long way. Class 3, if you had damage from a class 3 laser, it would cause serious eye injury. Now there's safety eyewear, which is not just for shards, although you should wear those when you fusion splicing. The safety eyewear that we're talking about is eyewear that will actually protect and isolate and actually block wavelength of those specific fiber wavelengths. So it's imperative that you wear the safety eyewear when you're doing these tests as well. They're not just cool looking glasses or for style. So, and as I said, the other items that you'd be coming across, VFL is, the red light that you're going to be using, the VFL is a class 2. Optical amplifiers 3, that would be an EDFA. Raman optical amplifiers, much higher energy coming from those. Those are class 3 or even 4. So let's look at some important practices. These are suggestions for optimizing your test equipment. So did you know that most problems in a fiber network come from the connector? So if it's damaged or dirty, it's not only going to affect the quality of the signal, but it can also damage your expensive equipment. As I already mentioned, like the OTDR bulkhead. In terms of measurements, reflected light from a dirty connector can actually destabilize the laser. Using dirty equipment can damage the elements, fiber test bulkheads, etc., and the connectors themselves. And dirty connectors will actually increase insertion loss as well, leading to lots of bit errors when you're making QAM measurements. Two things in terms of light. Too little light will lead to what we call a snow effect and increases bit error rates. Too much light will lead to a blooming effect on the video, like a very bright effect. So several things that can cause optical loss. All of these on the screen here can cause optical loss. Attenuation is it's mainly loss that occurs from faulty components. So you can see this in badly installed fiber. You can see this in dirty or damaged connectors and end faces. You can see this in poor quality fiber splices that produce higher than usual attenuation or like misaligned splices. You can see this in micro bends, which is fiber that's bent too much beyond the recommended bend radius. The other two things that cause optical loss is dispersion, and there's two different types of those. We've got chromatic dispersion. This is when this occurs when certain wavelengths will travel faster than the other wavelengths. So it's represented here on the left by different colors. So one wavelength will get ahead of the other one at a different time. Polarization mode dispersion. This is physically on different axes where it occurs when, so it's polarization of light in like a waveguide when these do not travel at the same speed as well due to random imperfections in the fiber. And you may or may not have heard this, but there's another term, birefringence in fiber. That's talking about the polarization issues that occur. So in general, these are the things you're going to need to check. So ensure that you have good fitting connectors and the end faces are not damaged. You'll need to measure fiber loss attenuation. You must confirm proper light levels. You want to identify and find any faults in the system, and you want to perform CWDM and DWDM verification. So let's look at some fiber scopes. So these ones here on the screen, these are displayed, these are all fiber scopes. The one on the right is an OTDR. And they're typically going to have a USB plug-in if they're an OTDR. Actually, I think most of them, if they have a dongle on them, they're going to be a USB plug-in. And then with the fiber scope, you're going to have different tips. So you might have a flat UPC, and you're going to have different tip sizes, as I already mentioned, like 1.25 and 2.5 millimeters. In addition, that APC, that angled tip, is available as well in one of these, but takes a lot more skill when you're trying to physically get it to align. If you do have an APC connector, you may plug it in and it's actually a dark screen. So you're going to have to turn it slightly. It takes a bit of skill, like I said, to be able to physically get it to be at the right angle for that tip, and then you'll see it appear. So you have to hold it kind of steady as well as you're displaying it. So always follow good cleaning practices. You've probably heard these a million times, certainly if you're a pro fiber tech, but use good quality wipes with alcohol, lint-free cloth, that's very important. One-click cleaners. They do a very decent job. They're easy to use. They typically do take more than one click, but don't click them multiple times. You'll be wasting it. I always remember when I visited a contractor many years ago, and we were talking about one-click cleaners, and he's like, "Oh yeah, we gave those to all of our fiber guys." He goes, "We had boxes of them, and by the end of the week we were done. They'd used them all." He goes, I guess I failed to tell them that they should only click once or twice. So be sure that if you're a manager, be sure you train your guys how to do the cleaning. So check the fiber interface with your fiber scope. Inspect both sides when you're doing a jumper. Don't take shortcuts. A visual inspection is going to reveal a whole lot, and you just cannot see this dirt by looking at it. I once purchased a fiber off the shelf. I'm sure you've heard of Fry's. We don't have Fry's anymore in Texas. It closed down, but I bought I needed to get some single mode fiber off the shelf, bought it. I did have a fiber scope, came back and plugged in a brand new connector into the fiber scope, and it was severely chipped right out of the bag. So these are the types of things you want to look for. The other thing is fiber optic connectors, typically they're physical contact, which means they're touching each other. And that's the other reason, if they're damaged, they're very capable of damaging the other side. So this is a perfectly clean connector. And to be honest, you're probably never going to see it this clean, but this is the goal, to be able to get it this clean. So I once walked into a training group, training some fiber techs, and I asked the question, how do you clean your fiber connectors? And the answer I got was, we clean them on our shirts. So, and I'm not kidding, this was a very decent sized company, and I was quite surprised. So many techs have not been adequately trained with regards to good cleaning techniques, issues associated with these types of cleaning. So let me play that again, because I love this. I love this. Breathing on it and rubbing it on the shirt. Do not be this guy. Airborne dust particles are the size of the core diameter of a single mode fiber. So removing a dust cap, these are just some things that you may not think about, but removing a dust cap can create static electricity, which in turn will attract dust. Yes, the dust cap is good, but you've got to be aware of what can happen. So the dust cap itself can also be the contaminated source. And after all, when last did you hear about somebody cleaning the dust cap, right? So a dust cap can contain dust, mold, and moisture. So never assume that if the fiber has a dust cap on and you pull it off, you're like, I cleaned it an hour ago, I'm ready to go. No, you're not. You have to still clean it again. If you drop a connector on a carpet, it's pretty deadly in terms of what it's going to do to the end of the fiber. It will probably damage the transmission path. So, make sure you clean that as well. Even just leaving a connector open, if you've cleaned it and you're sitting and leaving it open, even if no one's touched it, dust can still settle on it. So never touch the connector tip with your fingers. So this is one of the worst things you can do. We would kind of have fun with this when we were showing fiberscopes at cable shows. Sometimes we would think of all the things we could use to put contaminants on the end. And the easiest one was just touching your finger, or even worse, your forehead. And it would look just like this. So the oil residue will actually attract additional dust as well. And this is tough to get off. Trust me, it doesn't come off with a one-click cleaner, even if at least not easily. Usually several clicks will get it off, but you may have to go beyond a one-click cleaner if it's got grease or fingerprints on there. This one is a finger smudge. So the finger touched and then it moved along the outside. Honestly, you're only ever going to know what kind of contaminants and contamination you have on one of these with a fiberscope. So a little more on this. The contaminated connector here is more likely going to show dirt across this entire area. So the center area, or the core, right there, the core is the most critical part. But even if you have dirt on the edges, you're going to want to clean that, because that dirt can migrate itself physically to the inside. As it's touching the other connector and it's moving across, it can migrate towards the core. So even if you check it and you have a clean core, if it's anywhere inside the cladding area, you have to get that clean before you use it. Just 1 micron length of contaminant can be the difference between having an end face that meets or fails the recommended specifications. So a 5 to 6 millimeter micron in length can actually stop communication. So inspection on both sides, the core for dirt or permanent defects is important. Okay, so measuring loss and attenuation. So how to measure loss? You will be using a light source and an optical power meter. You'll be measuring the insertion loss of the fiber in dB, so decibels. This is a good test to do on certain discrete components, like let's say you've got cables or any component that is you're having to test the light from one place or one source to the other. You can use a light source and optical power meter. And the amount of fiber loss will determine the distance, and the data can be transmitted. Critical to make sure that the loss in the network stays within these design specifications. So once connected to a network, you'll no longer be able to physically insert a light source, but you'll still be able to check the correct power levels. And that's what you want to do. So if power is too low, you need to troubleshoot it and verify why you had that extra loss or attenuation. Obviously, there's other issues that occur. If the power is too high, you can have other issues too. You need to add attenuation. Too high, you could overdrive detectors, which can cause additional noise in the system and distortion too. And it actually can even damage a network device. So a little bit on VFLs, visual fault locators. So after doing the previous tests, if you still have a problem, a fault still needs to be found, of course. So for close-in environments, you can use a VFL like this. You can use it on a splice tray, for example. A visual fault locator like this is going to detect things like cracks or sharp bends. You can see that glowing light coming from there, that's what you're looking for. So typically it's good to kind of darken the space if you're looking for problems on there, but you're looking for micro, macro bends, all sorts of things that can occur. Pretty cool little tool, but obviously you will have to bring the network down to find it. Certainly you can use a VFL very effectively before you turn the network up as well. So let's talk about OTDRs. So there's two different modes in an OTDR. You have auto mode or manual mode. Auto mode obviously is easy to use. There's a lot of settings which take a lot of skill in terms of knowing what the right parameters are, like pulse width and different settings. So it makes sense to use the auto mode when you can, but don't use that as a shortcut. You really do want to learn these parameters in manual mode as well. So in the auto mode in general, this is what it's going to do. So you want to use auto mode. It's going to send a pulse with the longest pulse width first to determine the end of the fiber. That's step one. Then it uses the range and it automatically locates these events. If the trace is too noisy as it sent the pulse, you may need to use manual mode. And then if the trace has a strong back reflection, you'll probably have to use manual mode and then select the shorter pulse width. So in many cases, there's no shortcut. You'll still have to learn manual mode as well. So let's break down the OTDR trace a little bit. The slope of the trace, which is the y over the x, which is vertical over horizontal. This is going to determine the attenuation coefficient. So the first event here, which is a reflection, it's going to show the OTDR pulse width and the resolution. And we'll go into pulse width in the next few slides. So a loss like this, let's see, there's a splice loss as well. The last event here it's a fusion splice actually. And since good fusion splices, they're not usually reflective, but there will be a loss. You typically won't see a spike. The event is going to be measured in the same similar way. The event is actually measured from the beginning of where the pulse starts to turn up or down. So you're looking for three basic signatures. They're called reflective, non-reflective, and gain. And these are what are called a Fresnel reflection, and that's F-R-E-S-N-E-L, Fresnel reflection. And this is caused by light passing through two materials with a different index of refraction. So small portion of the light that is reflected is called a Fresnel. So that is the reflected light. And the reflected signature is always going to have that vertical spike that I mentioned upwards. Here's some more examples of different Fresnel reflections. So we've got a mechanical splice. These are typically good connections, even though they are mechanical. You might get a reflection that you may not get in an actual fusion splice. Just depends on the material. As you push the fibers into a mechanical splice, there's index matching gel, which is going to reduce that, but probably will only minimize the Fresnel reflection. It probably will not eliminate it. You're going to get an optical. This is a UPC connector, so you're going to get reflection because it's flat. If you'd used an APC, this would probably not even be there, be minimal. So that's the other reason I wanted to physically show this to you when we were talking about APC connectors. This is what you're trying to prevent using an APC, by using an APC. And the final one there is an open connector. Physically, it's unterminated. It's going to have the most significant reflection. So as you're working with different splitters, fiber splitters, there's two different kinds. There's one called a planar splitter and one called a fused biconical splitter. So FBT is the other one. So we'll talk about the FBT in the next slide. But This one here, the planar splitter is typically going to be the reflective kind. So this one is here. This is a non-reflective event. So typically this will be a fusion splice where the two fibers are fused together. It could also be a macro or a micro band. Typically, and then this is talking about the FTB, the fused biconical taper, where there's no reflection. You might see this in an FTB type splitter where no reflection, you're getting a little bit of loss as well. If you are operating in the wavelength range of like 850, 1310, 1550, you're probably using the traditional cheaper splitter, which is the planar type, the reflective kind. The FBT splitter is a lot more expensive. This one's called a gain, kind of unusual, but if you did see a loss on one side, it's not uncommon. If you're able to take the OTDR and shoot it from the other side, that might result in a gain if you're shooting it the other way. So Rayleigh scattering, this is the reflection of light. So light coming backwards towards the laser source. And basically it's a constant low level reflection. It's caused by the natural reflection and absorption inside the fiber. And this reflection is actually what is used to calculate the level of attenuation anyway. So it's a function of dB versus kilometers. And it is this backscattering level that physically gives us the ability to make those measurements. So it's just the physical dynamics of the fiber, but that's called Rayleigh backscattering. Oh yes, one other thing. So higher wavelengths, there will be less attenuation. Shorter ones use less power to travel over the same distance. So a little bit on pulse widths. The pulse width here is it's basically the time that the laser is on. And then that time that it's on is converted into distance. And then that, so that the pulse width has a physical length. So if you're using an OTDR, this pulse width carries the energy, the physical energy, and they're required to create the back reflection that you need to characterize the link. So the shorter the pulse, the less energy it carries, the shorter the distance it travels, and due to the loss. When the trace becomes noisy, of course, you would increase the acquisition time, and you could improve the signal to noise a little bit, and you could still maintain a good resolution. And then you would probably have to go to the next available higher pulse if that doesn't work. So changing pulse widths, you pretty much, the pulse width actually is going to be determining the minimum distance required to identify two separate events. So you've got two events here. You may or may not see them. So pulse width this is another way to look at pulse width. It's pretty much a trade-off. So the shorter pulse width, here's the shorter pulse width, you can identify close events, but you may not have enough power to go to the end of the fiber. The longer pulse width will have enough power to reach the end of the fiber, but may not be able to identify two closely spaced events. So you may have to play with those pulse widths to see those events. Dynamic range, another very important parameter. This is something that if you're looking for an OTDR for a specific function, you need to be aware of the dynamic range. So the bigger the dynamic range, the longer the distance can reach. So if you have a high dynamic range, you'd see a much higher number in terms of kilometers or miles that OTDR can measure. If you're working in a pond environment, you really do need a high dynamic range OTDR because you're going to be going through splitters. So if you're going through like 16, like a ratio splitter of 1 to 16, you would need at least a 34 dB 1 by 32, you'd need 35 dB at minimum, or even a 64, you'd need at least a 40 dB dynamic range to be able to work in that environment. A little bit about dead zones. There are two types of dead zones. There's attenuation dead zone and event dead zone, but that gets a little bit complicated. I don't want to go into that detail right now, but just for those of you newbies, if you're learning about dead zone, the way to think of it is just it's the length of time during which the detector is temporarily blinded. So it's got a high amount of reflected light and it's not able to physically see for that moment in time. And that once that time passes, it can then read the light again. And that physical time is then converted into distance. So just think of the dead zone physically as that area where you're not going to be able to measure anything correctly. So it's basically an area you want to avoid. So let's figure out how to fix that. If you're trying to measure something in that dead zone, like a short distance, you want to use something called a launch cable. And here's an example of two extremes. This one on the left is actually 10 kilometers. You probably don't need one that long, but a 500-meter one is certainly adequate for most applications. You're basically putting the launch cable in the beginning between your network and the OTDR, and the dead zone is going to occur inside the launch cable. So the minute you see that first reflection, that is going to be the beginning of your actual cable, and you'll need to move the markers accordingly and subtract the launch cable distance from the actual result. But that's conceptually, I just wanted to share. That's a very important piece. You need to be aware what the dead zone is on an OTDR. You need to read that or understand that specification. And if it's 5 to 10 meters, for example, and you're trying to measure close in, that would be a problem. Get yourself a launch cable. And last but not least, optical return loss. This is a measurement which is very important. It's going to show you the amount of reflection in your system. It's an important measurement for optical transmission. So since reflections can cause, it's going to, the higher the ORL, the more unstable the laser can become. So especially if you're testing and you're operating in a CWDM or DWDM environment, ORL measurements are particularly important. You're looking for the bigger the number is, the bigger the number, the better. You're looking for a number closer to -70, but it's a pretty wide range. It could be as high as -42, but that would be the minimum, or sorry, that would be the maximum reflectance limit. So somewhere in there, but ideally closer to 70. And those are the high levels of things I like to share about the foundational pieces that you need to understand with OTDRs, optical and fiber. So hopefully that was informative. And I'm going to hand this over to you, Andy, for questions.
Actually, currently there aren't any, but Nick Segura in the chat just asked a question of the group.
Of course he did.
So we'll give the group just a moment just to read that and see if anyone wants to comment.
Okay.
Actually, I'm sorry, maybe this question was to you. My apologies. Okay, so here's a question. So this is for you, Kendall. Cable operators are changing from analog fiber links to digital links in support of DAA and remote PHY. Is there anything we should be looking for that could bite us later? Change connectors, remove EDFAs, anything else? Thank you, Nick.
So I am just starting to learn more about that technology. I'll tell you what, I could certainly find out and let you know. But yeah, that will be a topic that I will be writing on over the next year. We'll be creating some new fiber courses on those new subjects. So, and I'll make that the first question that we address. How's that?
Ah, perfect. Hey, does fiber, does it have an age? You know, does it wear out ever? I mean, does it just, can it get brittle? Can it get stretched? Can it just become old and unusable?
You know, I actually don't know how long it could last, but I mean, I would expect you to get at least 20 years of use of fiber. I don't know what you think, Nick.
Oh, I don't want to comment on that so much as you know, it's fun to think that over 100
Yeah.
years something could change and PMD could be a problem, but I've not seen any examples or heard about examples. I have some splicing closures.
Honestly, yeah, I honestly don't know the age. I'm sure there's some deterioration. I mean, glass can actually change shape. You know, you look at an old pane of glass in a house, really old, let's say 100-year-old house. That glass is actually moved. It's actually melted, and not because of heat. It's just physically moved. I have to think that there's something like that that could occur in fiber over a long period of time.
I've also heard some war stories from technicians who, you know, in their history, 30-year history of fiber optic aliens, they found certain type of fiber types that were extremely brittle over time, and they would not touch it ever. But if you didn't know, you would compromise them pretty easy.
Right. Yeah, I'm sure there were different formulations of glass and how they made them. And certainly, I think if you were working with fiber in the early days of fiber, you might have some issues. But yeah, today's fiber, it's come a long, long way. I mean, we're dealing with fiber that has almost zero band radius, I mean, everything has changed. You're working with a much higher class of fiber. So, but again, I don't know the length of time that it would work for in the field.
Yeah, and some would ask, you know, does fiber freeze? And I think the answer is the glass itself does not freeze, but the introduction of moisture really causes an issue, such as got a picture of a splicing closure that a tech pulled the fiber out of, and it was a popsicle, right? It was encased in frozen ice, and that was a real issue. So in that case, freeze did affect fiber, but it was the ice and the pressure, not the actual moisture.
Right. Yeah, I'm sure you see some interesting things out there.
So here's another question. Once a fiber is landed to a MUX, a termination panel, or a transmitter or receiver, can they get dirty? I mean, they're connected and they're sealed. Can they get dirty? Is there ever a need to scope and clean them on a regular basis?
Well, and this, yeah, I mean, they can, and this would be from dirt that probably was inherently still in there. I mean, this is not an it's a tight seal, but it's not airtight. So you could probably get some dirt that settles somewhere on the edge and it's migrated towards the core. So I would say that's certainly possible. As you constantly are looking for power loss on these connectors in the future, yeah, you never want to assume that it's going to stay clean. That's for sure. But yeah, I mean, that picture that I showed you of what that core should look like, I guarantee you, you're always plugging it in with a certain small amount of dirt as best as you can clean it. But there's always going to be something that could migrate to the center of the core.
All right, do we have any other questions from the floor? The virtual floor?
Yeah.
All right, cool. Well, Kendall, thank you so very much for being our guest speaker this month.
My pleasure, Andrew.
NCTI has been a valued partner because you've helped us out twice this year and last year. So who knows? We'll keep that trend going.
Sounds good. Absolutely.
So I'm going to stop the recording and then thank you all for attending this month's last Thursday session for the Rocky Mountain chapter of the SCTE.